So, hello, Vikash. Vikash Mittal, are you around?
Hello.
Ah,
Yeah,
okay.
I'm here.
Yeah, you are now audible and you can share your screen.
Uh, okay, let me try.
So, let me introduce him first
Is,
formally.
is it
So,
visible?
Yeah, it's visible.
Yeah, thanks.
Hmm. So, Dr. Vikash Mittal is a research associate at Aizer Mohali. His research of interest is in geometrical phase, quantum walk, open quantum system, topological phase of matter. So today he is going to talk on geometric decomposition of geodesics and null-phase curve using Majorana star representation. So we are welcome you, Vikash Mittal. So stage is yours. You can start now.
Thank you so much. And let me take this opportunity to first thanks the organizer for putting up such a great program and giving me an opportunity to present my research work. And I hope I'm audible. And please stop me in case you have any question. Please feel free to do that. Okay. Okay. So let
Sorry for
me.
the interruption,
Yeah.
Vikash.
Yeah.
So few part of your slides are not visible actually. Those are getting outside of the screen.
Uh,
Yeah. I think you can discuss. Yes, that's fine now. Yeah,
it's visible now.
it's visible now. Now fine.
I think uh, yeah, now can you see the whole screen?
Yeah, now it's
Okay,
fine.
okay. Thanks for pointing. So, okay, get back on the track and let me start by introducing our group at Aisar Mohali. So, it's a group of Dr. Sandeep Goyal, and as and we have right now 5 PhD students. Chanchal Navdeep and Chanchal works in quantum memory, and she just submitted her thesis. She works in intra-frequency comms, quantum memories, quantum communication, and all those things. Another PhD student, Navdeep Arya, he also just submitted his thesis, and yesterday you might have heard his talk on non-inertial effects, and he works basically on the interface of quantum mechanics and gravity. Akhil is a new PhD student, and he started looking into the collective response of quantum systems in the presence of gravitational field, and this will be kind of continuation of Navdeep's work. Apart from this, there are two more new PhD students, Swaprajit and Rahul, and they are doing experimental work, uh, which is towards which involves generation and manipulation of orbital angular momentum modes, which is again from the perspective of quantum information, because these OM modes are very instrumental in quantum information processing. This is me, and this is our previous postdoc, Akhilesh KS. Right now, he's in Israel, and the work that I'm going to present is published in this paper, and which is done in collaboration with Akhilesh. Okay, so let's start. So here's a quick overview of my talk. So I'll start with the motivation, where I'll talk about the geometry of state space and how we can tackle the state spaces of higher dimensional quantum systems. Then I'll talk about this geometric representation, which is instrumental in studying the higher dimensional state spaces. And after that, I'll come to our results, which involves these two components. One is geodesics and one null-phase curves, which I'll explain as we go on. Just a second. Yes. And after that, I'll conclude. Okay. So with that, let's start with the motivation. So uh, uh, when we talk about, let's start by talking geometry of state space. So this is a diagram of which this community is very familiar with. This is a Bloch sphere, and a simplest system that we can think of in quantum information or quantum mechanics in general is two-level system. And any general state of a two-level system, rho, can be written in this form, where R is a real three-dimensional vector and sigmas are the Pauli matrices sigma x, sigma y, sigma z. R can be computed as the expectation value of these Pauli matrices. So this consists of all the states, all possible states of two-level system. So the state space of a two-level quantum system is a Bloch sphere, a three-dimensional Bloch sphere, where all the pure states lie on the sphere. As we can see here, we have 0 and 1, and on this equator, we have the states, eigenstates of sigma x and sigma y. And as we go inside, we are stuck with the mixed states, and the state at the center is maximally mixed state, which is for which R is equal to 0, and the rho is just half times identity. So in general, for an n-level quantum system, if you have an n-level quantum system, so the state space is n square minus one dimensional. For example, here we had a two-level quantum system, so the state space is three-dimensional Bloch sphere. And for example, even if you go one dimensional higher, for example, for a three-level system, the state space will be 8-dimensional, and which is very difficult to even visualize. People have tried getting around it by considering different facet and by projecting it on two-dimensional plane, but it's not easy. For the time being, we can handle 3, but as we go higher, so it's very difficult to visualize the system itself, forget about state space. So we get around, so there is one way, there is one representation. For example, when we represent our state by rho, this is one representation. We can represent our state by ket vector psi. So another representation, which is very instrumental, which is very beneficial when we are talking about higher dimensional Hilbert spaces, is something called Majorana star representation. So in this representation, it dates back to 1936, and at that time nobody noticed it, but then it started gaining popularity because of its application in quantum information processing. So the key idea in this representation is the dimension of the Hilbert space of n-level quantum system, Hn, is isomorphic to the symmetric subspace of n-1 two-level systems or qubits. And when we say symmetric, it's symmetric about the particle exchange. So for example, if you consider two qubit system, so the total Hilbert space will be 4-dimensional. And out of that 4, we can decompose that 4-dimensional Hilbert space into the symmetric subspace, which is of 3-dimensional, and the antisymmetric subspace, which is of 1-dimensional. And these are famous triplet and singlet. And if you can, we can see clearly. So when I say symmetric, so it is symmetric about the particle exchange. And as you can see, the symmetric subspace of 2 qubits is exactly 3-dimensional. And you can check, check so on. And there is a nullity theorem in linear algebra using which you can prove it directly. Okay, so for a 3-level system, a given general state psi 3 can be written as a linear superposition or symmetric superposition of psi 1 and psi 2, where psi 1 and psi 2 are the states of 2-level system qubit states. And these 2 qubit states, because we know for a qubit, it's very easy to visualize it in terms of Bloch sphere, and each state of a qubit represent a point on a Bloch sphere. So a general state, any general state of 3-level system can be decomposed, can be written as a linear symmetric superposition of the states of 2 qubits, and these 2 qubit states correspond to 2 points on a Bloch sphere, and these are called Majorana stars. And the collection of these Majorana stars is something considered as Majorana constellation. We can extend this idea to an n-level system. For an n-level system, similarly, we can write it as a symmetric superposition, symmetric combination of this psi 1, psi 2, and up to psi n-1 of n-1 two-level states, where the summation is over all the symmetric permutations which we can think of. And any general state of an n-level system correspond to n-1 points, which are given by these psi 1, psi 2, psi n-1 small size on the Bloch sphere. Now, having said that, now we have a way to tackle the higher dimensional, to deal the higher dimensional Hilbert space. Now, the first object under consideration is something called geodesics. So I'll understand, like I'll discuss like why geodesics are important and why are we considering it. But in the beginning, let's just
hello. Excuse me.
Yeah, is there a question?
Yeah, just a quick question. Like for the Majorana star representation, it is for symmetric states. So do you think
Mhm.
is there any kind of representation for asymmetric states like this singlets
No.
and
No. You this is not what I said. So when we say uh, so this Merner star representation, so you can take any state. For example, this I3, it can be any state. It has nothing to do with whether it is symmetric or antisymmetric, but it can always be decomposed in a symmetric combination of these n-1 qubits. For example, here. So when we say symmetric states, so it is the symmetric states of the n-1 qubits, not the system itself. Okay. So the state under consideration, for example, if you have a 3-level system and you have a general state alpha, beta, gamma, doesn't matter whether it needs to be symmetric or not symmetric. You can write that alpha, beta, gamma as a symmetric combination of such things with some proper coefficient which are function of alpha, beta, gamma.
Okay, yeah. Thank you.
Okay. Yeah. Okay, so okay, we are at the geodesics. So I was introducing geodesics. So geodesics is the shortest curve between any two given point on a surface. This is how we define a geodesic, not the other way around. For example, if you have a Bloch sphere or any general sphere given any 2 points A and B, so this red line represents a geodesic as it is the shortest distance between A and B, shortest curve connecting these 2 points. However, when people talk about geodesics and the mathematical definition, so this other path which I have shown in the right picture is also, it qualifies also as a geodesic. However, in our work, whenever we mean geodesic, so we meant by a minimal geodesic, which is given in the left. So mathematicians sometimes call it minimal geodesic or the shortest geodesics, to be precise. But we only meant the minimal geodesic, not the other one. Okay. So for a given curve psi s with some parameter s, we fix the two endpoints s1 and s2, and these correspond to let's say two end states psi1 and psi2, which are like psi s1 and psi s2, and so we can find a geodesic connecting these two states psi1 and psi2 by solving this differential equation, second order differential equation, which results in a solution like this. It is a very simple differential equation, and if you look carefully, it is nothing but a differential equation of a one-dimensional harmonic oscillator. So the solution of this differential equation will be some linear combination of sine and cosine functions. You can this whole analysis can be found in this reference by Simon and Mukunda. It's a paper analysis in physics titled Quantum Kinetic Approach to Geometric Phase. So this is the curve which is a geodesic connecting states psi1 and psi2. Okay. So, and as we know, geodesics appear very frequently in the theory of gravitation when we talk about this linear curved spacetime. Apart from that, you can find the role of geodesics in quantum computation. Basically, we have an initial state and we want to go to some target state. So when we do the calculation, it comes out, it boils down to finding the geodesic between these two states. So in that sense, geodesics are instrumental in quantum computation, and also the geometric processing like the surface remeshing and the computational architecture. And you'll be amazed to know that these geodesics appear very frequently in these remeshing techniques, which are used in gaming industries nowadays, and to enrich the experience, to take that whole experience of gaming to the next level. So geodesics play a very integral role there in that industry also. Apart from these exotic properties, geodesics has one more interesting properties, which is that if we have a system which is evolving along a geodesic, our system does not acquire any additional geometric phase. So let's say if we have a system which is prepared in a state psi A, and we go to state psi B and then C and then come back to A, where all these individual points are connected by a geodesic, then the geometric phase, by using this property of a geodesic that the system does not acquire any geometric phase, we can write the expression of geometric phase as this quantity, where this delta 3 is given by the cyclic relation and known as Bargman invariant. So in this conference in itself, there was a very nice talk by Vivek Vyas from IIIT Ranchi, and he explained the fundamentals of geometric phase and geodesic, and he talked in length. So you can please, I would suggest you to refer to that talk. But here I'll just say a few words regarding geometric phase. So let's consider a state, initial state, and some n0, and we take that state around a closed loop, and that closed loop is in some parameter space on which our Hamiltonian depends. So this is the formulation by Barry. So if we take this state very slowly, so according to the adiabatic theorem, our state remains in the same, our system remains in the instantaneous eigenstate of the Hamiltonian, and it changes up to an overall phase factor only. So after a complete circle, when we come back, our state is same as the initial state, and apart from this overall phase factor. However, this overall phase factor has two contributions. One is the dynamical contribution, which depends on the evolution of the system or the energy eigenstate, or how fast, how slow you are moving. And apart from that, there is another factor which is of geometric origin, which is given by this, and the formal expression for this geometric phase was given by Barry as this integral. So this expression was given in 1983, but the early signatures of geometric phase can be seen as long as in 1956 due to Panchratnam. So in standard quantum mechanics, we generally study this dynamical phase, and which is of no importance because it is an overall phase and we cannot measure it. But geometric phase is non-integral phase, and we can measure it in the experiments. Okay, so this is about the geodesic. Now what we do is we take a geodesic in a 3-level system or 3-dimensional system. So we fix 2 states. We take 2 states to be psi 1 and psi 2. We connect them by a geodesic, which is given by psi s. And now, since we have seen that any given state can be represented by n-1 points. So for example, a state of a 3-level system can be represented by 2 points on a Bloch sphere. So a smooth curve in a 3-level system, in a 3-dimensional system, can be decomposed into 2 curves, 2 smooth curves on the Bloch sphere. So this is a curve in 3-dimensional, in a 3-level system, and it can be decomposed into 2 curves, chi0 and chi1 on the Bloch sphere, where all these factors are, these are like some mathematics, state-of-the-art mathematics, which is of not importance right now. So now what we do is, and since we get this curve chi0, it's a state of a qubit as a function of this parameter s. Using this state, we can always find a Bloch vector, and let's plot that Bloch vector on the Bloch sphere. So this blue curve is chi0, and it is a curve as goes from some initial value to final value, and this orange curve corresponds to chi1, and the general state is given by the symmetric superposition of these two. And you can see this end state 0, 0 and 5, 5, and it's not like the point of taking the end state of this form is just for the simplicity, so that our curve is closed and we can understand it and we can study it. We can take any general 2 end states and we can connect it by geodesic. However, in our paper we have shown explicitly that any given 2 states can be brought to these forms by using appropriate geometry. So one of the advantage of using this kind of form is we get these degenerate Majorana star. So 2 Majorana star corresponding to this state will lie on the same point. Same is for this end state. Now by looking at it, if we look closely, so it looks like a complete circle, and it does not look like it. We have confirmed it by finding an equation. So that equation, the equation of this component, and together these 2 curves satisfy this equation with the center at alpha beta 0 and alpha square, and the radius is beta square. Remember, alpha beta are coming from this end state. So these are 2 curves just by changing the end states, and now we extend it to this n-dimensional state space. Similarly, for an n-dimensional system, we take 2 end states to be n-fold degenerate states, And here are the results, main results of our work. So for a given n-level system, we correspondingly we get n-1 curves, or more precisely circular segments, as we have seen in earlier pictures. Now, depending on whether n is odd or even, we get different results. So for example, if n is odd, we get n-1 over 2 dual pairs. And what do we mean by dual pairs? So the curves which are reflection of each other by some axis, so we call them dual pair, dual curves or dual pair. So for example, this is this result is for 3-dimensional system, and 3 minus 1 over 2 is 1, so we get exactly one dual pair. And if n is even, in that case we get n-2 over 2 dual pairs, and in addition to that we get one curve which is along the great circle. So in this case, this is for 4-dimensional system. You can see for a 4-level system we get n-1, that is 3 curves, 3 circular segments, and this blue and orange one, they form a dual pair, and this yellow one is along a great circle, and it's this additional curve. So further we can see, so it's the 4-dimensional system, it's 5-dimensional, and it is for 6-dimensional, and it goes on. But we can generalize it. You don't have to plot everything. So when you generalize it, you will find that these curves, these circular segments are not arbitrary. These are unique, because the one uniqueness is coming from the fact that for a given state, a Majorana decomposition is unique for a given state. And when we take some state to n states, we go to the Majorana decomposition. That decomposition is unique. So these curves, these circular segments comes with a unique radius and unique center. So by doing the reverse engineering, you can always find a geodesic in higher dimensional Hilbert space by taking into consider these circular segments of appropriate radius and center. So this way we can study the geodesics in higher dimensional Hilbert space simply using the Bloch sphere, simply on the Bloch sphere by using Majorana star decomposition. And why is it necessary to study geodesics? For example, as far as state space is concerned. So for example, if I give you an information that I have a system, and the geodesics of that system are arcs of a great circle. So by given this information, we can infer that the state space of that system might be sphere, because we know the geodesics on a sphere are the curves, are the segments of the great circle. In that way, these are integral from the perspective of quantum information and in general to study the state space. Now we ask the reverse question, because we talked about a very integral property of geodesics, that when our system is evolving along a geodesic curve, it does not acquire any geometric phase. Now we ask the reverse question, that if given a curve and we compile our system in such a way that it does not acquire any geometric phase, does it need to be a geodesic? The answer comes out to be no. So there is a larger class of curve along which, if our system evolves, it does not acquire any geometric phase, and geodesics are just a subset of it. So earlier we saw an expression involving 3 discrete states, but if we have n discrete states, so for that we can write this Bargmann invariant, this cyclic inequality, as this, and the geometric phase for such a case is given by this expression, by the argument of this Bargmann invariant. It is given by Pancharatnam, and it's known as Pancharatnam connection. Now the interesting thing is, for example, if we have 4 discrete states, psi 1, psi 2, psi 3, psi 4, and given any 4 states, we can always write a Bargmann or Bargmann invariant of 4th order. And it is very easy to show that 4th order Bargmann invariant can be further divided into Bargmann order of order 3rd. So in that sense, if we have n discrete states, and this is the Bargmann invariant, this cyclic relation, this cyclic expression, and which is known as Bargmann invariant nth order, this can always be broken down into segments of 3rd order Bargmann invariant. So it is actually the 3rd order Bargmann invariant is the fundamental quantity of interest, and for a given curve, smooth curve psi s again, and where s is the parameter going from s1 to s2, if we can satisfy this condition, what we are saying in this condition, that if we take a third order Bargman invariant anywhere on the curve, so this has to be real and positive, such that if you take the argument of it will always vanish, it will always be 0. So in that case, we can form a null-phase curve. So what we do is, we do the same analysis, since we understand now that null-phase curves is a bigger class of curves and geodesics are just a subset, so it is very natural to understand and to study the geometric decomposition of NPCs in three-dimensional state space, or not just not just three-dimensional, but to higher dimensional also. So here we find very interesting property, and it's a kind of proposition that if we take any curve and if we take the dual of that curve, if you can see psi s and psi prime s, they are dual of each other, because if you see there is a minus sign here, so the rx and ry, x and z component of these two curves will be same, the Bloch component of these two curves will be same, they only differ by y component, which is the opposite of it. So using these two dual curves, we can form a null-phase curve, and it is very easy to show explicitly that this curve satisfies this property 7. Okay, and now we consider an explicit example of this form. We take this IS, which is given by this, where GS is cos SS minus theta. Theta is decided by the endpoints, and S is the parameter which is going from 0 to theta. So when we decompose it using Majorana decomposition, this curve, so it decomposes it same as, because since it is a three-dimensional curve, it decomposes to two curves. And as we can see, a contrasting difference between the decomposition of a geodesic and a null-phase curve. Geodesic decomposes to the circular segment, and together they form a complete circle, and they are dual of each other. However, in this case, we can see the duality, they are reflection of each other, but they are not circular segments anymore. And if you can see clearly from here, it is clear that when I made this proposition, that if you take any curve connecting these two endpoints and you take any dual curve, you can form a NPC. And just by extrapolating this same statement, we can show very easily that the NPC between any two given 2 points are not unique. However, geodesic between any two given points is a unique curve. So we have infinite number of NPCs between given any 2 points, and one of them is a geodesic, which satisfies the certain differential equation. Okay, so this is the last part, and with this I conclude. We developed a Bloch sphere decomposition for geodesics and null-phase curves in higher dimensional Hilbert spaces, which are these two components are the key ingredients in understanding the fundamental structure of geometric phase. And we considered geodesics connecting two n-1 fold degenerate Majorana states, and which decompose to n-1 circular segments, and the behavior and the distribution of these circular segments depends on the dimension, whether it is odd or even. Same we did with NPCs, and we saw that we can construct NPC by using any pair of dual curve between the instants. And this is with this I end my talk, and I thank all the audience for listening. And I would be happy to take any questions.
So thanks. It was a very nice talk, Vikash. So our session is now open for question and answer. So participant, you can ask the question now.
So I have a question. So in this case, like any higher dimensional state can be represented through these geodesics on the Bloch sphere, right? So is it the right understanding?
No. So any given state can be represented by points on the Bloch sphere.
Okay. And
okay. So for example, if you have a 3-level state of a 3-level system, so that state can be represented by precisely 2 points on the Bloch sphere.
Okay. Okay.
Yeah.
Okay. So is it always on the surface of the Bloch sphere, or there may be cases where it lies inside the Bloch sphere, like for pure and mixed states?
No, it always lies on the surface of the Bloch sphere, because the state under consideration in higher dimensional space is pure state.
Okay, I see.
Yeah,
Okay.
because for mixed state it is complicated and still it is not very convenient or very well settled down. But people have tried for giving a Majorana star decomposition for mixed state, but the arguments are not very convincing. So right now I'm not sure how to deal with that. But this our analysis was concerned about the pure states.
Okay, nice. Thank you.
Any other question? So if it is not, then we can move to our next talk. So thanks again, Vikash.
Thank you so much.
It was really good and very beautiful talk.